Okay, get this. Imagine AI generating images so vast and so detailed that when you zoom into what looks like just a single pixel,
Oh, wow.
it reveals a perfectly rendered cell-on, like a digital pathology slide or a car and a satellite image stretching across miles. It's kind of mind-blowing, right?
Yeah.
If you find this stuff as fascinating as we do, hit that subscribe button to support the channel. We're diving deep into some incredible AI breakthroughs.
What really grabs me is how they've managed to achieve this massive scale without compromising on detail. AI has always struggled to create images that are both huge and incredibly detailed, maintaining that level of detail across the entire image.
Yeah, exactly. That's what we're exploring today. We're going to unpack this new research on ZoomLDM. It's a new kind of latent diffusion model that's kind of changing the game for generating these truly gigantic high-resolution images.
I mean, just think about the possibilities. Imagine the potential for, incredibly accurate cancer diagnoses using these super detailed digital pathology images, or even drastically improved environmental monitoring with satellite imagery that covers vast areas but doesn't skimp on the details.
Right. So the main source for today's deep dive is this research paper that introduces ZoomLDM. You also send over some interesting thoughts on storytelling, which we'll definitely keep in mind as we unpack this pretty complex but potentially revolutionary development.
It's going to be exciting to see how it all connects.
So our mission today is pretty straightforward. We want to demystify the core ideas behind ZoomLDM. We want you to walk away with a solid understanding of how it actually works and why it's such a big deal for the future of large-scale image generation with AI.
And how this might impact various fields.
Exactly. So
Yeah.
to kind of set the stage a bit, if you look at the history of AI research, there's always been this drive to handle increasingly complex data.
Right.
And large high-resolution images, they represent a kind of frontier in that journey.
Absolutely.
Okay, so let me try to illustrate this with an analogy. Imagine you're trying to create a colossal mosaic. We're talking massive, right? So large that you need to step way back to even see the entire design. But here's the thing. Each individual tile in this mosaic is also this tiny masterpiece of detail.
Oh, I like that. Okay.
Right. Now think about older AI models. They often face this tough trade-off. They could either generate those beautiful, detailed individual tiles.
Like focusing on the small pieces.
Yeah, but then struggle to assemble them into a coherent, larger picture. Or they could capture the overall structure of the mosaic, but with blurry, undefined individual tiles.
So it's either high detail or large scale, but not both.
Yeah, it's been difficult to achieve both.
Hmm?
So this brings us to the central question. How can AI create these incredibly large images where you have both fine-grained accuracy at a local level, meaning those individual tiles are perfect, and overall consistency across the entire canvas, even when it's tens of thousands of pixels in each dimension?
That's the million-dollar question, isn't it?
It really is. And that's where ZoomLDM comes in. It offers this new approach that tries to create those perfectly detailed tiles and also make sure they all fit together seamlessly to form this vast, coherent mosaic. It's like tackling the microscopic and the macroscopic at the same time.
It sounds like quite a feat.
Yeah, it is. So before we jump into how ZoomLDM actually achieves this, it's important to understand why directly generating these massive images has been such a challenge in the first place. Let's take a digital pathology slide as an example. These images can easily reach dimensions of like 32,000 by 32,000 pixels or even larger.
Wow, that's enormous.
It is. Now imagine trying to train an AI model directly on images of that size. It would require an insane amount of computational power and data. It's simply not feasible with the technology we have today.
Yeah, it's like trying to run a supercomputer on a smartphone battery.
Exactly. So in the past, researchers tried to get around this by generating smaller image patches, say 256 by 256 pixels.
Kind of breaking the problem down.
Yeah, and then stitching them together to create the larger image. But, this patch-based approach had its downsides.
And the paper actually shows this really well. Figure 1 visually demonstrates the limitations of these earlier patch-based methods. You can clearly see that while individual patches might look okay on their own, the final composite images end up blurry, lacking this overall cohesive structure.
Right, it's like having a puzzle where the individual pieces are beautiful, but they don't actually fit together to form a recognizable image. You might zoom in on some cells, and they look pretty realistic, but then the overall tissue architecture is completely off. Or in a satellite image, you might have detailed roads that suddenly end abruptly or don't connect in a logical way when you zoom out to see the bigger picture.
It's like sentences without paragraphs, words without a story.
Yeah, exactly. And if we think about the real-world applications of this, This lack of global context is a major problem. In pathology, for example, the spatial arrangement of different tissue types is crucial for making an accurate diagnosis.
Right. And in satellite imagery, you need to understand the relationships between different geographical features to do things like effective environmental monitoring.
Exactly. So losing that broader context really limits how useful those generated images can be. And it's not just the pixel count that's a challenge. Obtaining detailed annotations for these huge images is another major obstacle.
Yeah, imagine having to label every single cell in a gigapixel pathology slide.
It would be a nightmare. Right.
Absolutely. Plus, as the paper points out, even the meaning of a label can change depending on the zoom level you're looking at. Like, labeling a region as water in a zoomed-out satellite view could refer to an entire lake, but if you zoom in closer, it might actually be a narrow river.
So that raises a crucial question. How do you train an AI to understand and generate these multi-scale images effectively without relying on these time-consuming and scale-dependent annotations?
Right, it's a real chicken and egg situation. You need the annotations to train the AI, but getting those annotations at that scale is practically impossible.
And that's where ZoomLDM's innovative multi-scale approach really shines. The core idea is that it's not just focused on creating those small patches, it's learning to comprehend and generate image content across a whole range of zoom levels, all at the same time. It can handle those tiny thumbnail views and those larger, more detailed sections while always maintaining an awareness of the overall structure. Figure 1 really highlights how ZoomLDM can generate patches at multiple scales, right?
Yeah.
Creating those large images we talked about and even doing super resolution.
I see. So it's not just about generating individual pieces, it's about understanding the relationships between those pieces at different scales.
Exactly. And the way it does this is through something called magnification-aware conditioning. The model isn't just processing pixels blindly. It has an understanding of the scale it's working at.
So it knows whether it's zoomed in close or looking at the bigger picture, and it adjusts its generation process accordingly.
Exactly. And that allows it to generate the appropriate level of detail for each specific zoom level, while also being informed by the information that's present at other scales.
Makes sense.
Now, to get around the problem of needing tons of manual annotations, ZoomLDM utilizes what are called Self-Supervised Learning Embeddings, or SSL embeddings. Basically, these are AI models that have already been trained to extract meaningful features from images without needing those explicit human-made labels.
Clever. So it's using pre-trained models to kind of bootstrap its understanding of the images?
Exactly. And specifically for the histopathology images, they used a model called UNI, which was pre-trained on patches at 20x magnification. And for the satellite images, they used another powerful model called DOV2.
So these pre-trained models provide ZoomLDM with a rich set of features to work with.
They do. Okay, now we're getting to the part that I find really cool. The heart of ZoomLDM is this novel idea of a shared latent space. They call it the cross-magnification latent space. So picture this. It's like an abstract space where the AI can represent those visual features it's extracting from all those different zoom levels in a unified way.
Interesting. So instead of treating each scale as a separate entity, it's bringing them all together into this common space.
Exactly. And the key here is that those feature representations from different scales, they're not isolated. They're all projected into this common space, which allows the model to learn the intricate relationships and dependencies between what it sees at different magnifications of the same underlying content. Figure 2 in the paper gives a really helpful visual overview of this.
So it's learning how the microscopic details connect to the macroscopic structure and vice versa.
Yes. And to actually create this shared latent space, they developed what's called a summarizer module. Think of it like a super sophisticated system, a trainable transformer that takes those SSL embeddings from different scales and processes them.
So it's kind of like a chef who takes all these different ingredients and blends them together to create a unique flavor profile.
That's a great analogy. And the summarizer isn't just looking at the embeddings themselves, it also takes the magnification level as a direct input.
Meaning it knows how zoomed in or zoomed out the information is?
Exactly. So it's scale aware, meaning it understands whether it's dealing with a highly zoomed in view or a more zoomed out perspective, and it can adjust its process accordingly.
Oh, that makes a lot of sense.
Right. This awareness of scale is really key to the model's ability to generate images with the right level of detail at each magnification. It's not just about identifying visual features. It's about understanding how those features manifest and relate to each other at different zoom levels.
So it's not just what, it's also where. in the context of the zoom level.
Exactly. Now, what if you want to generate completely new images from scratch without having an existing image to extract those SSL embeddings from? That's where the conditioning diffusion model, or CDM, comes in.
So this is how you move beyond just recreating or manipulating existing images. You can actually generate new ones entirely.
Right. The CDM is basically another diffusion model, but its job isn't to directly generate images. Its purpose is to learn how to sample from that cross-magnification latent space that we talked about. It learns all the patterns and relationships within that space, but it does this based on the specific scale you want to generate.
So it's learning the rules of that shared space.
Yeah, exactly. And Figure S5 in the supplementary material shows how the summarizer and the CDM work together. So once ZoomLDM has learned this space, the CDM can navigate it and generate new sets of those summarized embeddings, which the main ZoomLDM can then use to create completely novel images at different scales. It's like having a recipe generator that can come up with new combinations of ingredients based on the type of dish you want to make.
That's a fantastic analogy.
Thanks. Now, what's really impressive about the CDM is how data efficient it is. The paper highlights that it can generate high-quality, unique images even at scales where the training data was pretty limited.
Wow, so it's not just memorizing the images it's seen, it's actually generalizing and coming up with new stuff.
Exactly. Like, they were able to generate believable thumbnail images at a very low magnification, 0.15625x, with only about 2,500 training images. That's pretty remarkable. And it suggests that the model is really learning the structure of that cross-magnification latent space, not just memorizing specific images. You can explore that further in Figure S10.
That's really exciting because it means that this approach could be applied in areas where you don't have huge amounts of labeled data, which is often the case in scientific and medical fields.
Absolutely. Okay, now let's get to the really crucial part. How does ZoomLDM actually go about generating those large, coherent images? Well, this is where their innovative joint multi-scale sampling approach comes in. Remember that mosaic analogy we talked about? The core idea here is that they're generating the image content at different scales at the same time.
So it's not doing it piece by piece, it's doing it all at once.
In a way, yeah. Think of it like this. The model starts by generating a low-resolution context image. This coarser image captures the basic structure and arrangement of the scene.
So it's like creating a rough sketch before adding the details.
Exactly. And then this lower resolution image acts as a guide for generating higher resolution detail patches within that broader context. So instead of trying to generate the entire high resolution image in one shot, which would be computationally demanding and could lead to inconsistencies, it uses a lower resolution version as a blueprint to make sure all the high resolution parts fit together properly and maintain that overall global context.
It's a really smart way to manage the complexity.
It is. Now, this simultaneous generation across different scales does present a challenge. How do you ensure that all the details in those high-resolution patches line up perfectly with the structural information from the lower-resolution context image? It's like making sure that the patterns on your mosaic tiles flow smoothly across the entire design.
Yeah, I can see how that would be tricky.
The paper gets into the math behind this, mentioning a downsampling operator A in equation 1, and a modified conditional inference algorithm, which you can find details on in algorithm S2 of the supplementary material.
We don't need to get bogged down in the equations, but the main takeaway is...
Yeah, the main takeaway is that they use a self-guidance mechanism. It's like the information from different scales is constantly talking to each other, informing and refining the image generation at other scales throughout the process.
So it's a constant feedback loop, making sure everything stays consistent.
Exactly. And the results are really impressive. Look at Figure 3 and Figures S14 and S15. They show how ZoomLDM can generate these coherent histopathology images at resolutions up to 4096 by 4096 pixels.
Wow, that's massive.
It is. And when you compare these to previous efforts, like Grykos et al. 17 and Taprush 26, which are shown in Figures S16 and S17, you can see a noticeable difference. ZoomLDM strikes a much better balance between capturing those fine details and maintaining the global coherence of the image.
And Table 3 even shows that ZoomLDM is significantly faster at generating these large images compared to previous methods.
Right, so it's not just more accurate, it's also more efficient. Now, here's something that I thought was really cool. They found that ZoomLDM can also be used for super resolution.
Oh, interesting. So you can take a low-resolution image and increase its resolution to reveal more detail.
Exactly. And what's fascinating is that they didn't specifically train the model to do super resolution. This capability just emerged naturally from its multi-scale training. But there is a challenge here. When you're given a low-resolution image, You don't have those high magnification SSL embeddings that the model usually relies on for conditioning, especially in the histopathology domain.
So how do they work around that?
Well, they discovered something they call an inversion property. They developed this technique, kind of inspired by textual inversion, that lets them essentially infer the missing conditioning embeddings from the low-resolution image. It's like trying to figure out the original blueprint of a building just by looking at a blurry photo of the finished structure.
I see. So it's using the available information to estimate what the missing information would likely be.
Yeah. And figures S8 and S9 in the supplementary material illustrate how they do this. And the results are pretty amazing. Table 4 and Figure 4 show that ZoomLDM produces really high-quality, super-resolution images. It maintains the fidelity of the original image while adding in those sharper details. In many cases, it even outperforms AI models that were specifically designed for super-resolution.
That's really impressive.
It is. So we've seen how ZoomLDM can generate these amazing large-scale images and even do super resolution. But what about real-world applications beyond just creating pretty pictures? This is where it gets really interesting. The researchers explored using ZoomLDM to extract meaningful features from histopathology images for some pretty important medical tasks, like identifying different types of cancer, which is called subtyping.
Subtyping is crucial for determining the best course of treatment.
Absolutely. They also looked at predicting something called homologous recombination deficiency, or HRD, which is a biomarker that helps guide treatment decisions for cancer patients. Now, traditionally, if you wanted to extract these multi-scale features for tasks like this, you would need to train separate AI models for each magnification level.
That sounds very inefficient.
It can be. But because ZoomLDM is trained across multiple scales, you can extract these features seamlessly from a single model. And that's a big deal.
So it's not just about generating images, it's also about extracting valuable information from those images and doing it in a more efficient way.
Exactly. And the results are pretty compelling. Table 5 shows that ZoomLDM's multi-scale features outperformed other state-of-the-art vision encoders on these medical tasks. These encoders include FICON, UNI, and C-Transpath.
Those are all pretty big names in the field.
They are. What's even more interesting is that even when they extracted features from ZoomLDM at just a single magnification, like 20x, those features were often still better than the other encoders. That suggests that by training across multiple scales, ZoomLDM learns more informative representations overall.
It's like having a more holistic understanding of the images, which translates into better performance on these tasks.
Right. So to kind of sum up the key takeaways here, ZoomLDM represents a significant step forward in generating these large, high-resolution images. It does this by learning and understanding visual information across multiple scales simultaneously. And the cross-magnification latent space and that innovative summarizer module are really at the heart of its ability to capture both the broad context and the fine-grained detail.
And importantly, it can generate new, high-quality images even when it doesn't have a lot of training data at certain scales. Plus, we saw how it can be applied to real-world tasks like super resolution and medical image analysis.
Of course, no model is perfect. The researchers do acknowledge some limitations. For example, when it's generating very large areas with uniform visual characteristics, you might still notice subtle spitching artifacts where those generated patches come together.
So it's not completely seamless in every situation.
Right. And maintaining perfect coherence across scales for extremely fine, thin structures can still be a challenge.
Makes sense.
Yeah. They discuss some of these nuances in relation to Figure S14 and the supplementary material, but overall, this research is really exciting. They talk about it laying the foundation for what they call foundation generative models in fields like histopathology.
Oh, that's an interesting term.
It is, and it's really thought-provoking. Imagine AI being able to generate these realistic variations of tumor tissue at different stages of development or with different characteristics. It could revolutionize our understanding of tumor heterogeneity.
It could help us classify cancers more accurately and potentially even lead to more targeted therapies.
Exactly. And in their conclusion, they even hint at the possibility of incorporating other types of data, like text descriptions or RNA sequencing data, into this framework.
That would be amazing. It could really open up a whole new world of possibilities for research and applications.
I think so, too. So here's a final thought for you to consider as we wrap up this deep dive. Now that AI has the power to generate this kind of incredibly detailed and contextually rich visual information, especially in scientific and medical fields, what new discoveries or diagnostic tools might become possible as these current limitations are overcome?
It's a question that's worth pondering. This exploration of ZoomLDM is just the beginning, and there's so much more to discover and understand in this rapidly advancing field.
Absolutely. There's a lot to be excited about.